We now make a slight transition in our study of continuity. When we looked at graphs of a function, it's pretty clear whether a function is continuous or not. If it has a break, it's not. If it's drawn with one pen stroke, it is continuous. What happens if we just have a formula, though? Let's take a look at this exotic-looking function y equals sine of x over x and ask about its continuity. All right. Where is the obvious concern? Well, this dividing by 0. If we divide by 0 at x equals 0, something weird is happening there. However, it certainly is continuous at a few points that we can identify. When x is positive, well, we have sine x over some positive number, and we know sine x is continuous. And these positive numbers are all fine. And so this is all going to be defined everywhere for x greater than 0, and will also be continuous. This is going to change gradually. Our positive number in the bottom is going to change gradually. So overall, it's going to be a continuous function as well. There's a lot of theory behind all this, and if you're interested in that, Math 120 is a course that delves much more deeply into the technical side of this, the proofs, rather than the qualitative statements here. So we can make this more rigorous if we want to. But for now, the intuition is probably enough. So what happens if we look at x less than 0? Well, same kind of thing happens. We have a continuous function over another continuous function here, some negative values, but it's still continuous. And so this is also going to be well defined and continuous as well. However, we could have a discontinuity at x equals 0. What our analysis shows then is that everything's dandy for x positive, everything's dandy for x negative in terms of continuity, but at 0 there might be something suspicious happening, and that's what we're going to explore next. So one of the ways to get our minds around this is to go back to our basic graphing techniques. What does this graph look like? It's a combination of a sine graph with a scaling factor. Well, if you don't know how to graph something, the obvious thing to do first is get some test points and see what they look like. Before we do that, though, one very, very, very important reminder. In any calculus class, we always use radians as our measure for the angles in sine, cosine, and all the trig functions. The reason is all the derivative rules that we're going to see later require, insist, demand that radians be the units, not degrees. So make sure your calculator's in radians. If you don't know how to change it, talk to a friend or talk to a TA or your instructor. All right, so with our calculator set to radians, we can do some sample points and just see what we get. So let's do a range here, and we'll zoom in around 1. And yeah, let's get a little bit closer than that. Okay. So if we plug in values in this range here, you're going to get numbers back, again, if you're in radians, that look like this, rounded off to 2 digits. For the moment, no, though when we get this close, we get to 0.998. And the nice thing that we see is if we go to x values that are positive, we actually get the same sign back. So let's do a little sketch of this. Put 0 in the middle. And these numbers are getting very, very close to 1. So let's put 1 at the top here. There. And what do we got? That's 0.5, 0.75, so 0.84 is about here. Let's make that -1. And 0.96 is here. 0.98 would be just below 0.99. Okay, that's what we're talking about. We've got a graph that looks like this, and looking at the pattern we see, the symmetry here, we're going to have the same kind of thing happening on the positive x side. So this is our x1, and this is our y value. And that's all smooth looking, except we know that at x equals 0, there's going to be a problem. Sine of 0 over 0, that's 0 over 0. That's one, we cannot actually divide by 0 and get a value back. That's illegal. Anytime we have a divide by 0, we're not going to get a specific value back. We might explore it differently later on, but when we try to plug in a value here, we're going to get an error in our calculator, or we'd call it an undefined point for our function. And that's what we're going to translate as the open circle here. So this graph is going to have a little break. It's going to be fine, it's going to be fine, it's going to be fine. Then just at x equals 0, it's like a hole was punched out of the function, and then it would resume as if it hadn't been interrupted with the smooth graph afterwards. So here we see it's continuous when x is less than 0, continuous when x is larger than 0, with just a little break in the middle. Okay, so it is not continuous. However, it's pretty well behaved. So this is different from 1 over x, where we have asymptotes. Here the graph is doing fine, doing fine, doing fine, and if it wasn't for this silly little hole, we would say, well, the graph is approaching, or that y approaches y equals 1 as x approaches 0. If we were just to ignore this little point here and just say, hey, where am I going following this graph? Then the answer would clearly be y equals 1. Well, in fact, that kind of statement's really important, so we formalize it in a nice mathematical formula or expression. What we say here is, instead of as x approaches 0, we say the limit as x approaches 0. Or, to make this a full sentence, in the limit as x approaches 0, and then we say, well, what is x doing? Well, it's going to be plugged into this function sine x over x. So in the limit as x approaches 0, actually, I rephrased that incorrectly. It's better to say the limit as x approaches 0 of sine of x over x is or equals. And here notice it's a bit different. We're actually going to say equals 1. So the limit is 1. Where would we end up if we were to continue towards 0, closer and closer? We would actually call the limit value 1. That's where we would end up if it wasn't for the hole. We'll explore that further in the next few sets of notes.